Well, here we are, our first video of distance learning. And depending on whether or not you're in my first period or my last period, you're used to hearing a different greeting, so I guess I'll go ahead and hit you both. Good morning, class, and good afternoon, class. We're starting calculus today, AP Calculus. And hopefully you can see that I've completely skipped over Chapter 1, because Chapter 1 is nothing but pre-calc review, stuff that you need to know to be able to do this crap. So we're just going to jump right into Chapter 2, and hopefully, even though we're all stuck at home and learning in this strange way, we can get through Chapter 2 and at least put a dent in Chapter 3, because we need to learn some of that stuff. Fingers crossed. We'll just see where it goes. I'm going to go ahead and apologize in advance for my video creating abilities. They're not the best, and you already know my handwriting sucks, but I think you're going to be surprised at how bad it is on paper. Either way, yeah, try to follow. My wife is laughing in the background. Try to follow along with me, and if you get lost anywhere along the way, feel free to shoot me a remind. Maybe even pause the video, shoot me a remind right then and there. I could even pull the video up and explain what was going on, maybe if I need to. Just you don't have the ability to ask me questions while I'm teaching, so you're going to have to really make sure you stay in contact with me, okay? All right, so what are we doing? We're starting with finding average speed. And really what we're talking about when we say average speed, we're talking about an average rate of change. Now, this is an Algebra 1 concept, average rate of change. It's really just the slope between any 2 points on a curve. So it says a rock breaks loose from the top of a tall cliff. What is the average speed during the first 2 seconds of fall? Well, I mean, to even start this question, you have to know how fast things fall. So we say that things fall like, and for those of you that in physics, this won't be anything new. We'll say h of t equals 16t squared. So yeah, things are going to fall at the 16t squared. This is going to be the acceleration due to gravity. I know that normally in physics it's negative because things are falling down, but since we're talking about the speed of this object, its speed is going to be growing, so we're going to use positive 16t squared. So average rate of speed. Average speed. I don't know. Maybe I need a rock star. Anyway, average speed. What we're going to have to do is figure out what the speed was when we began. So that's at time equals 0. And what the speed is at time equals 2. And all we're going to do to figure those two numbers out is plug in our t-values right here. So it shouldn't be too much of a stretch to believe that when you began, your speed was 0. And for this one, you plug in 2, you have 16 times 2 squared, which is 16 times 4, or 64. So we have our beginning coordinate as 0, 0, and our ending coordinate as 2, 64. Now along the way, clearly the speed was changing constantly. The object was speeding up from 0 all the way up to 64. But we want to know what was the average along the way. So you literally just used good old slope formula. Let's see if I can squeeze it in over here. M equals y2 minus y1 over x2 minus x1, because that's all the average rate of change is. It's legitimately the slope between 2 random points on a curve. You just connect the dots, draw a straight line. What is that straight line slope? Boom, there, right there. So we have our average speed equals, oops, wrong variable, my apologies, h of 2 minus h of 0, this is y2 minus y1, over 2 minus 0, that's x2 minus x1, scoot my clipboard over, gives us 64 minus 0 over 2 minus 0, or 32. So our average speed was 32 feet per second. There we go. That's not that bad, right? I mean, this is clearly a curve, right? It's a parabola. If you graph it, and if you connect these 2 dots on that parabola with a straight line, this would be that straight line slope. Pretty neat. You see, calculus deals a lot with rates of change, deals a lot with slopes, specifically of curves. What do you mean a slope of a curve? Well, you're going to see very soon that it's possible to find an instantaneous rate of change, meaning a slope at a single point. We're not going to learn all the rules yet. This is just baby steps. So what is the speed of the rock at the instant time equals 2? It's not 32. I mean, 32 is the average speed, right? I mean, yeah, we know it's 64, but suspend belief for a moment. We have a curve, a parabola, 16t squared, and every single point on that curve, we could say it has a slope. So let's talk about how we can find the slope of a curve at a single point. Well, Mr. M, how are you supposed to do that? I mean, you just said in order to find the slope, you need 2 points, an x2, x1, y2, y1. How could we do it at a single point? And I go, okay, well, how about this? Imagine we have a number ridiculously close to 2. So we have one of our values, 2, and the other number is just, it's so close to 2, I can't even describe it numerically. So how about we say that the second point, oops, wrong variable again, the second point, t sub 2, if this is t sub 1, is 2 plus some minute value that we'll just call h. It's so small we can't even give it a numeric value, we can only give it a letter value, h. So this point, as long as h is positive, would be just a hair to the right of time equals 2. Just a hair. So let's find the average, in quotations, speed between these two t values. Well, up here, you saw me plug in the second t value. This is my second t value. So when we plug it in, we have, uh-oh, I used h twice, didn't I? I know how to fix that. Capital H, there we go. Let's use capital H's everywhere. Found another one. There we go. I'm on a capital H hunt. There they are. Sorry about the double letter there, folks. So don't get confused by this. This is not the same H that we had up here. So capital H was our height with respect to time. Lowercase h is some unimaginably small distance away from 2. There we go. All right. So when you're plugging in t sub 2, it's going to look like this. And then you're subtracting, you plugging in t sub 1, which, remember, we're calling 2 this time, over t sub 2 minus t sub 1. You see, we're just filling out this slope formula again. But we have to plug these things into 16t squared. So that's going to give me 16 times 2 plus h squared minus 16 times 2 squared. All over, well, here, the parentheses weren't necessary. I only used them so you could see that I was doing t2 minus t1. But when you combine your like terms, these two 2's cancel, and you're left with just an h. Let's see what happens. I'm going to assume by now everybody in the room, or I guess we're not in the room anymore, everybody at home knows how to FOIL, so t plus h squared means t plus h, 2 plus h times 2 plus h, which would be 4 plus 4h plus h squared, minus this right here is going to be 64. And we're still over h. Distribute your 16. 64 plus 64h plus 16h squared minus 64. Dropping the parentheses now since I've done my distribution, over h. Now we can combine our like terms. Check it out. These two 64s, oh, you know what? We can get fancy on you. Grab a colored pen. These two 64s cancel out. So what's left here is 64h plus 16h squared. Well, that factors. I'm just going to pull the h out, though. You're going to see why in just a second. So let me pull h as a GCF off that top, leaving me 64 plus 16h, all divided by h. Whoa! Check it out. Those h's cancel. That means you're left with the average rate of change, the instantaneous speed, being 64 plus 16h. So you're looking at this and you're going, Mr. M, that's not a speed. What kind of a result is that? Well, remember I said that h is an unimaginably small distance away from 2. So why don't we say it's so small that it's essentially equal to 0? Let's just pretend it's so small we have to call it 0. And if you do that, this would be 16 times 0, which would head towards the value of just 0, telling us that the slope, also known as instantaneous rate of change of our parabola, is 64 at time equals 2. You just found the slope of a single point. Neato mosquito. So that's just a small taste of what we're going to be doing going forward. This lesson is going to require us to introduce the concept of the limit. You see, what I did here was pretend h was so close to 0 that we had to pretend it equaled 0. In actuality, what I was asking you to do was find a limit as the value h approached 0. So we've got some pretty complex mumbo jumbo right here. And rather than read it, you know what? Check this out. Don't even worry about that, okay? Let me just explain to you what it says. It says, as your x values approach a wanted number, your y values approach another number. We call that a limit. So if you have a curve and your x's are getting close to some numeric value, an actual real number, if the y values are also heading towards a real number value, then you say that that real number value, that real number y value, is a limit. And this is how you set it up. So again, we read it as the limit as x heads towards some number, our y values head towards this number, and this number L would be called the limit. That's why they used capital L. Important little tidbit of information right here. Let's find the limit as x approaches 0 of this function. What this means is, what value are my y's approaching as my x's get really close to 0? When we were working on this example, you saw me say, hey, why don't we just call h 0? And I've dropped in h equals 0 and the whole thing disappeared. Yeah, you can't do that here because you are not allowed to divide by 0. So what do? Well, I've told you to use a graph. So let me reach over. Handy dandy technology. Whoa, that's bright. See if I can avoid the lights and the shadow. Boom, look at that. Okay. Y equals, I've got it typed in already. Let's watch what happens. It's riveting. Okay, well, we can see, by the way, my y values, my scale is 1s. So this y value right here, that's at y equals 1. Now, the graphing calculator can't show you, but this graph doesn't exist at x equals 0. Proving it to you. See, error. The graph doesn't exist at 0, but sure looks like it does, right? That's because it has a limit. So basically, as our x values get closer and closer to 0, and I'm talking about from both sides, as x gets closer and closer and closer to 0, the y values are getting closer and closer and closer to 1. That means the limit as x approaches 0 of sine x over x equals 1. This is a really important fact. You're going to need to know it. In general, the limit as x approaches 0 of sine of ax over bx is just going to be equal to a over b. That's just a fact that I need you to memorize right now. Cool beans? Cool beans. Okay, flip them over. I think I hit the mic with the papers, sorry. So here I've got 3 different pictures of almost the same function. Okay? And what we're talking about is what's happening to our limits as we get close to certain types of discontinuities. You see right here, I have a hole in my graph. Right here, I don't have a hole. Instead, I have a removable discontinuity that has come down here. And then right here, I just have a straight line without a hole at all, no discontinuity whatsoever. So what's going on here? Well, f of 1 does not exist. We can see that it's a hole in the graph, error on graphing calculator. However, as my x's approach the value 1 from both sides, my y values are approaching the value of 2. Can it get there? No. You see, a limit is a goal. It can't actually get to 2 because that point doesn't exist on my graph. However, its goal is the y value of 2. So we say the limit is 2. The point doesn't have to exist for it to be the limit. Let's look at the next one. F of 1 is 1. It's right here. There's f of 1. But the limit, as my x's get closer and closer and closer to 1, is crashing into the value y equals 2. Remember, a limit is a goal. So the graph doesn't have to exist at that point like you saw here for that to be the limit. And guess what? The graph could exist somewhere completely different than what the limit actually is. Because if you looked at the number 0.9999999 and you looked at the number 1.0001 and you asked the graphing calculator what the y value was, you would get numbers dangerously close to 2 on both sides. So we can then say that the limit as x approaches 1 of this function is also 2. And then on this one, this last one, which doesn't even have a discontinuity, yeah, f of 1 is 2 because it's a solid line. And I hope it really doesn't break anybody's brains without me drawing the red and blue arrows for me to say the limit as x approaches 1 is 2, because again, as I get closer and closer to here, I'm getting closer and closer to here. So there it is. Limits are goals. They describe where the y values are heading as x gets close to a number from both sides of that number. So limits have some pretty simple and familiar properties. We're just going to scoot these notes on up. Lots of properties. Let's see, what does it say? If L, M, C, and K are real numbers, okay. So what we're saying here is the limit as x approaches C of f of x is L. So this is the limit of f of x. And the limit as x approaches C of g of x is M. See, M is the limit of g of x. The sum rule says if you're trying to find the limit of 2 functions being added, you can just add those limits. And because of that, the difference rule says, yeah, if you're trying to find the limit of function minus function, then it's just first limit minus second limit. It should be pretty easy. Product rule does exactly what you think it would do. The limit, when you find the product of 2 functions, is the product of the 2 functions' limits. Constant multiplier rule says k is a constant, remember, so if I have like 2 times f of x, like a vertical stretch, what that would do is it would vertically stretch my limit, so to speak. So it's just following regular old mathematical rules that you're familiar with. Quotient rule, yeah, it works exactly as you would think. So if I'm doing function divided by function and I try to find its limit, then it's always going to be limit divided by limit, as long as, of course, capital M doesn't equal 0, because then you would have a discontinuity on your hands, right? And the last one is the power rule that says you can raise the function to any kind of weird rational number, a fraction. The limit of the function would just be the limit raised to the same rational fraction, as long as that's a real number, obviously. For example, -2 raised to the 1/2. You can't do that. It's imaginary. Okay? All right. So the rules are not alien. They're exactly what you would hope they would be, which is good news for us. Flipping it over, and yep, that is the end of these notes right here. Great. So it says, use these observations and the property of limits to find this limit of this polynomial and this limit of this rational function. This says the limit as x approaches c of a constant is just that constant. That means who cares what number you're approaching, it's just a constant value. It's not changing at all. And this says the limit as x approaches c of x just equals c, and the reason why is because you're allowed to plug c in without creating any kind of discontinuity. So this says like, yo, you've got a straight line, like this one. What happens when you plug in 1? Yeah, you get exactly what you think you would get. So you go, okay, as x approaches 2 of this function, my answer would be 2. Whoop, you can't even see what I'm pointing at. My apologies. As x approaches 2 of this function, you would just get 2. That's all that says. So the first one, it's got a plus and it's got a minus. It's got some exponents. So what we're going to be doing is we're going to be combining the power rules and the sum and difference rules for A. The limit as x approaches c of f of x, we're calling this f of x, by the way, is, let's split it up. The limit as x approaches c of x cubed plus the limit as x approaches c of 4x squared minus, nope, plus, excuse me, the limit as x approaches c of -3. There's my minus sign right there. Well, if you plug in c right here, you get no discontinuities. If you plug in c right here, you get no discontinuities. And if you plug in c right, oh, you can't. It's a constant. See? Ta-da! That row right there. So it's just -3. Basically, what you just learned is if you have a smooth polynomial, a smooth curve with no discontinuities at all, then all you have to do to find your limit is literally plug the x value in. Boom. Now this one's got a possibility of discontinuities because rational function. A possibility. So for part B, let's call this g of x. The limit as x approaches c of g of x, well, it's a fraction. So I can use my quotient rule. I can do the limit of the top divided by the limit of the bottom. And let's use the logic that we found right up here. As long as you have a polynomial that does not have discontinuities, you can literally drop your constant in for x. Oh, look, a polynomial. It's not going to have any discontinuities, so I can just drop this c everywhere I see an x. C to the 4th plus c squared minus 1. And guess what? X squared plus 5. There's no discontinuities there, so once again, you can just drop c in. C squared plus 5. Pow. There you go. Shouldn't be that bad. So what's going on down here? Polynomial and rational functions. Wow, it's almost like we just dealt with those. So if f of x is some kind of polynomial and c is any real number, then if you would like to find the limit as x approaches c of that polynomial, you literally just plug in c for x. That's all that's telling you to do, and then it's showing you everywhere had an x it plugged in c. And then down here it says if f of x and g of x are polynomials and c is any real number, then, well, since they're both polynomials, they should both follow this rule, right? Yeah. So you can literally drop c in there and c in there, and you get that. And that, of course, is as long as plugging in c doesn't give you a 0. Remember, c is any number I want it to be. So this is what we just did in fancy math terms. So somebody probably got famous for doing that. Okie dokie smoky. Down here and we're going to be done in just a second. Sorry it's taking so long, guys. X squared 2 minus x. Yeah, I can just plug in 3 here. No discontinuities. This is going to be a smooth curve. So the limit as x approaches 3 of x squared times 2 minus x is literally 3 squared times 2 minus 3, or 9 times negative 1. Whew, breaking a sweat. No, I'm not. That was A. And then part B. The only time I would ever have a problem here is if I was trying to plug in the value -2, but I'm not. So guess what? Smooth curve. Plugging this in doesn't give me a 0 on the bottom. So literally, the limit as x approaches 2 of ugly rational function is just 2 squared plus 2 times 2 plus 4. I should have put that in parentheses. Over 2 plus 2. And this gives me 12 over 4, which is 3. And there it is. Your intro to limits. I'm sorry it took so long, guys. Hopefully future notes don't ever take this long again. Like I said, send me a remind if you need to ask me any kinds of questions. Your first assignment for this material is on the MyMathLab platform. I think it's only 10 questions long. I'm going to continue to try to use MyMathLab for all of your homework on this. I believe I called it DL number 1, meaning distance learning number 1 assignment. I'm pretty sure I'll be able to pull this off. All right, so hit me up with any questions, and I'll be talking to you soon. All right, bye, guys.